So in today's video, we're going to talk about acid bases. This is part 2, and really this is the setup for video 3. What we're going to do today is really going to lay the groundwork for video 3, and the goal in video 3 is that you can look at different materials, look at their structure, and identify that if this material was put in water, would it make that water acidic, basic, and would it be a strong acid, a strong base, a weak acid, or a weak base? Okay, just to review real quick, we talked about this in the first video, that the general definition for acid and base is what we call an Arrhenius acid and base definition. An acid is something that gives up a free proton or an H plus ion, which we call the hydronium ion. It's sometimes described as an H3O plus because that H plus associates with water and makes an H3O plus. A base is basically something that gives up a hydroxide ion in solution. So hydrochloric acid, drop it in water, it's going to give up a hydronium ion and chloride counter ion. Sodium hydroxide, you drop it in water, gives up sodium cation, but the hydroxide anion, which is what defines it as a base according to Arrhenius. Just a reminder again that the fact that we're using H3O or H+, those are fairly interchangeable. So here's the second definition. Brønsted-Lowry kept the definition for the acid the same, that in solution something gives up a proton, but he considered a base to be something different. It was how it interacted with that proton. So an acid is something that donates an H+, therefore it has to have H in its formula. So all Arrhenius acids are Brønsted-Lowry acids. But a base is a substance that accepts a proton. But there are other materials that are able to accept protons besides a hydroxide. According to Brønsted-Lowry, those also are considered bases. So going back to the acid, that's standard HCl, as we expect, gives up a proton. That makes it an acid. Sodium hydroxide, as we'd expect, gives up a hydroxide, but according to Brønsted-Lowry, it's not whether it creates a hydroxide in solution, it's whether that hydroxide or whatever it is able to accept a proton. So in this example, yes it does. The hydroxide accepts a proton off of HCl and makes water. So that's what defines it as a base. And just to give a counterexample, here's a material, bicarbonate ion, that has no hydroxide in its structure, but it also is able to accept a proton off of water, make carbonic acid, and as a result, it makes the solution basic. It's a proton transfer process. In other words, it's not limited to water, and one way you might identify these bases is they have unpaired electrons. That's what allows them to accept the H plus ion. Here's a third definition. This is Lewis acid and bases. So this basically breaks free from the proton exchange altogether and says, well, let's focus on that electron pair. An acid is any substance that accepts an electron pair. So if you think about an H plus ion, it would certainly accept an electron pair from a hydroxide. Base is anything that donates an electron pair. So the Lewis acid base, you basically are defined by whether you can accept or donate a pair of electrons. And here's another example where this doesn't directly affect the pH of the solution. If you take an iron 3 plus ion, it is ready to accept electrons. The lone pair of electrons in the water actually coordinate to the iron, 6 of them in fact. And so in this definition, the electron donor is the water. That makes it a base. And the electron acceptor is the iron 3 plus ion, which is makes it the acid. And once again, this particular reaction, as drawn right to this point, is neither has not affected the pH of the solution. Now later we'll learn that this iron hexa-aqua complex can therefore move forward and make the water acidic through a different pathway, which we'll talk about here in a second. Okay, the other concept in here is that we refer to things as strong acids, strong bases, weak acids, weak bases. Let me just give you a very quick overview, and that is when you say it's a strong acid, it means it completely dissociates in water. HCl is a good example. If you looked at the equilibrium, it's much greater than 1. If you were to dissolve 4 moles per liter of HCl molecules, then you would create 4 moles of H plus ions. A strong base would have the same property. If you took sodium hydroxide, which is a strong base, and you dissolve 4 moles of sodium hydroxide in a liter of water, once again the equilibrium constant is much greater than 1. And if you dissolve 4 moles of sodium hydroxide, you'd end up with 4 moles of hydroxide ion in a liter of water. Completely disassociates. And the take home here with strong acids and strong bases, whatever the concentration of the starting material is, that is the concentration of either the proton or the hydroxide ion in solution. So here's some common acids and bases. Here's apple cider vinegar, which is predominantly acetic acid. It's a weak acid, obviously, because we're able to eat it. But if you had a strong acid, that would be like muriatic acid. Obviously, you can't eat that. Burn a hole in your mouth. But here's the deal. They both release protons. It's just the weak one does not favor an equilibrium going to the right where it releases protons. The strong completely disassociates. By the same token, if you go down to the base section, you might have a weak base such as bicarbonate, which creates very few hydroxide ions when it's dissolved in water. Or you might have a very strong base like oven cleaner, okay, which is sodium hydroxide. And so it completely dissociates and releases hydroxide ions. So going back to the acetic acid example, if you take acetic acid, you drop it in water, it creates some hydronium ions. That's why it's acidic. But the truth of the matter is it's weak, so that it predominantly stays together, so the pH of the solution doesn't lower. So if you dissolve 4 moles of acetic acid in a liter of water, you would get a lot less than 4 molar protons. In fact, you would get, and we'll learn how to calculate this later, 0.0085 molar hydronium ions. Here's another weak acid, and this will get you oriented. As we talked about earlier, the aluminum hexaaqua complex actually has the ability to make water acidic, so this is a different step, or a further step. Very small, highly charged metal ions, we're going to introduce you to this at first, have the ability to delocalize these electrons that are in the bond between oxygen and hydrogen, so it starts to weaken that bond. So consequently, that makes that positive. It's going more like a hydronium ion, and it can jump off onto the water and create H3O. So these are actually slightly weakly acidic solutions, highly charged metal ions, small highly charged metal ions. But once again, if you had 1 mole per liter of aluminum 3 ion and you dropped it in 1 mole in a liter of water, you wouldn't end up with 1 mole of hydronium ion. You'd actually get 0.003 moles. And once again, the exact calculation we'll learn later. Okay, a weak base, same story. Now there's 2 ways to get to a weak base. This nickel hydroxide is obviously a base. It has hydroxide in solution. But as we know from our solubility rules, nickel hydroxide is not soluble, so an insoluble metal hydroxide would actually be a source of a weak base. So if you drop 4 molar nickel hydroxide in solution, you would end up with 0.000016 molar hydroxide ions. And this particular calculation you could go back and do from the equilibrium section using KSP. Now another material that will make the pH change is a Brønsted-Lowry base, like ammonia. You drop it in water, it creates ammonium ions, and there's some hydroxide released. If you had 4 molar ammonia and you dropped it into water, the hydroxide concentration would be 0.000048 molar. And we'll learn to calculate this from the KB for this particular material later. But for right now, just the general idea that, look, if it's a weak base, it stays far to the left and doesn't create much hydroxide ion in solution. So where's the line between strong and weak besides just a qualitative measure? If you want to quantitatively measure it, you don't use pH, because I certainly could take a very strong acid, dissolve it in water, but dissolve very little of it, like in this example 1 × 10⁻⁶ molar, And then I have a very weakly acidic solution, but that's only because I dissolve very little acid. A better measure of whether something completely dissociates or not is the Ka, which basically is the equilibrium expression. And instead of just using the K, we have the subscript A to mean the acid dissociation equilibrium expression. And to understand this, sometimes we represent the acid just generically as HA. And I just want to remind you that that A does not represent acid, it represents an anion, because when an acid dissolves in water, it frees up a hydronium ion and the anion. They both go into solution. And if it shifts hard to the right, then it's a strong acid. If it stays back to the left, it's a weak acid. If you set up the equilibrium expression, it'll look like this, and this is where the Ka comes into play. But sometimes, much like pH, these numbers are, you want to see the magnitude of the number, and as opposed to the actual number itself. In other words, it's to the 4th power, the 5th power, the minus 3rd power. So you take the log of it, as we learned in the first videos. And so sometimes you'll hear things described by their pKa, which is taking the K to the minus log of the Ka. And analogous to the Ka for bases, there is the Kb, which is the base dissociation constant. Sets up the same way. We use the lowercase b because we don't want you to be confused with boron. Drop it in water. You create this cationic material, but you also free up a hydroxide ion that was released from the water. Okay, this leads to the expression. It's just a simple equilibrium expression with products over reactants. And once again, this also can be expressed logarithmically. So where's the line? Let's focus on the acid first. And I've set up basically a table that if I had an original acid concentration of 1 molar, and if I had an acid, for example, that had a pK of 14, it would have very little H plus in solution, so it's very strong to the left. If I had 1 molar of an acid with a pKa of 6, now I'm getting a little more H plus built up. But the real question is, where does complete dissociation happen? Well, if it's a 1 molar solution, then that complete dissociation happens whenever the H plus concentration starts to hit 1, and if you search down here, that happens down here below 0. So this is where 1 molar HA starts to fully dissociate. pKa of -1. Nitric acid fits in that category. Sulfuric acid, a known strong acid, has a Ka of 1 times 10 to the minus, or 1 times 10 to the 3, which gives it a pKa of a -3. And then the Ka of HCl, that occurs somewhere around times 10 to the 6th. So it's strongly dissociating. And the same thing with bases. If you set these up, whether it's a base that interacts with water, kind of this Brønsted-Lowry type base that creates hydroxide ions from the water, or it's a true hydroxide, like an Arrhenius base, which frees up hydroxide ions, you'd still set it up with this Kb. And the same story, that basically if you had an undissociated or a weak base, it would have a pKb. Now we're going to describe it in the pKb form of somewhere around 4. If that dropped less than 1, it would be completely dissociated. And some materials like that, which we call strong bases, are sodium hydroxide and lithium hydroxide. Okay, so now here's the objective. If you were given a lineup of materials, whether they were ammonia or you have salts or you have molecules, and the question is, if they were dropped in water, would it make that water strongly acidic, strongly basic, weakly acidic, or weakly basic? And what I'm asking about there is, will it completely disassociate or will it just barely disassociate? And I want you to be able to do that qualitatively based on structure. Okay? But before we do that, we have to make some definitions. There's some things you need to understand. So the first one is, you need to understand what a conjugate acid-base pair is. So in this example, To define a conjugate acid-base pair, let's start with acetic acid. It's obviously our conjugate acid. And when it loses its proton, it becomes the conjugate base, because you can imagine that this acetate ion has the ability to pick up a proton from somebody. It's a Lewis base, basically. It can accept a proton. So it is now a base. So the pairing is whatever was acidic when you remove the proton, it's a conjugate base. By the same token, if you take water, it now accepts a proton and it is now protonated. So before it was in this particular reaction, it acted like a base, like a Lewis base, but if you protonated, it is now the conjugate acid. So conjugate acid bases come in pairs like this. It's kind of like twins. You can't say you're a twin if there's only one person involved. There's got to be a person just like that somewhere. So conjugate acid bases are in pairs. So here's another example. So let's see if we can break this apart. First off, if you start with ammonia, it ended up with ammonium, so it accepted a proton. So this must be a base, right? But by the same token, once it's accepted the proton, it is now the conjugate acid. So we look at water in this situation. Okay, it gave up a proton. In this case, it's an acid, right? And when you look at it after it's deprotonated, it could certainly accept a proton, so it's now a base. Now, this is a good example that water can act as either a conjugate base or a conjugate acid. And you might go, well, gosh, how do I know which it is? Well, you have to look at what it's paired with and how it acts in the reaction to answer that question. So if I was just out of the clear blue to say, hey, is water a conjugate acid or conjugate base? You don't know. You have to see what reaction it's in. But for one pair, start at the reactants, move to products. The species that loses the proton, that's the conjugate acid. The species after it's lost its proton, that's the conjugate base. So here's a chance for you to practice. You need to work on this so you can identify those. I recommend that you stop your video, look at these species, make sure you study what they are before the reaction and after the reaction. Ask yourself whether they accepted a proton or gave up a proton, and identify the conjugate acid-base pairs. So pause your video, try and solve these problems, and when you're done, you can restart the video and check your answers. Okay, well, let's see how you did. Starting on the first one, did you see that when you started over here, the nitrate gave up a proton, so it must be the conjugate acid. Consequently, the nitrite ion, or the nitrate ion, could accept a proton going back, so it's a conjugate base. So we get over here to this other species. Here's a phosphate. It accepted the proton, so it must be consequently a base. But once it has the proton on it, the hydrogen phosphate ion, it is now a conjugate acid. And that's a conjugate acid relative, okay, to this conjugate base. The second reaction, carbonate accepted the proton, so it's a base. Its paired conjugate acid is over here. Here's back to water again. We know it could go either way, but in this particular case it gave up a proton, so that makes it acidic. So the conjugate acid, or the conjugate base, is going to be the hydroxide. So now we come down here to the last one, the hypochlorite ion. And if you look between where it started and where it ended up as a product, it accepted a proton, so it's the base. The ammonium cation gave up a proton, so it must be the acid. And over here, the ammonia would be the conjugate base to that acid. All right, good. Now, conjugate acid bases have related Kas and Kbs. Now, this is going to be very helpful for you later in calculations. I just wanted to jump off now since we'd already discussed Kas and Kbs and help you understand that. So let's walk through the proof for this. If you take ammonia and you put it in the presence of water, it's going to become the ammonium ion and hydroxide's left over. Consequently, if I took this ammonium ion, cation, and I isolated it and dropped it in water, it could accept or give up that proton as an acid and create the hydronium ion and ammonia back. And that has some Ka. Now the Kb we knew, because we'd already talked about that you can look this up in a table. But we don't know the ammonium Ka, but we do know this. Let's stack these equations and add them together. We've learned that in past videos with equilibrium. Cancel out what's common, which in this case the ammonia is common to both. The ammonium is also common to both, right? And then you collect all your terms and you get, oh, this looks familiar. This is water disassociating. We learned that in the last video. That actually is, has a K, what we call the Kw. It has an equilibrium constant of 1 times 10 to the 14th. And if we added these equations, remember that you can therefore multiply their equilibrium constants. And so now what you've done is you've said, oh, I can always relate the Ka to the Kb of, and this is a key, please catch this, of a conjugate acid-base pair. This is not any Ka to any Kb. It's the Ka or the Kb of a conjugate base to the Ka of its conjugate acid, and vice versa, are related by multiplying those together, and you get the Kw of water. Consequently, as we've learned with logarithms, if you're multiplying those together, you could take the pKa and add it to the pKb, and you should come up with the pK of water, okay, which is 14. All right, so let's practice that, what we've just learned, and see if you can solve for this. Here's a material that looks like it's acetic acid. It has a K of 1.8 times 10 to the minus 5. See if you can find the pKa. See if you can find the Kb of its conjugate base, and consequently, can you find the pKb for that? Then let's drop down to this another type of base. This is methyl ammonium. So it's very similar in structure to ammonia. It has a pKb of 3.4. Can you find the Kb? Can you also consequently find out the pKa of this particular base's conjugate acid, which is the methyl ammonium cation? And consequently, if you know its pKa, can you find its Ka? So once again, I'm going to remind you that relationship is right here. Okay, you can either multiply Ka times Kb and get the Kw of water, or you can add them together and get the pK of water. Stop your video, try and see if you can solve these, and when you're done, we'll restart the video and check your solutions. So how'd you do? Okay, remember, if you know the Ka, you can relate it to the pKa. It's minus log of the Ka equals the pKa. 4.7. Okay, the Kb of the conjugate base for this particular acid can be related by dividing it into the Ka of water, and I'm showing the actual how you might enter this in the calculator. It comes out 5.6 times 10 to the minus 10. So consequently, and I also made a note in here, you probably don't have acetate anion floating by itself, so it's probably in there as a salt. So for example, if I dropped in sodium acetate and I wondered how basic it is, I can find the Kb of that if I knew the Ka of the conjugate acid. Okay, if I know the Kb, I can turn it into the pKb based on that relationship that the pKa plus the pKb has to equal 14, so I can do a little algebra, re-manipulate that and get 9.3. So let's see how you did with methyl ammonia. Got to find the Kb based on the pKb. Now I need to unwind it, put the negative sign on it, raise it to the power of base 10. I solve it 4 times 10 to the minus 4. Turn that into a pKa. I can simply just subtract that pKb from 14. Once again, that's the conjugate acid-base pair. I get 11. If I did it exactly on the calculator to 3 significant figures, I get 10.6, but because I'm entering 2, I might record it as 11. When I go to find the Ka, I might raise that. I'm putting all 3 figures just so it's not confusing, but mathematically, if I put in negative 11, that would be correct to the significant figures. And I get somewhere around 2.5 times 10 to the minus 11. Okay, secondly, here's a little note about organic acids and bases, mostly covalent bonding. An organic acid, I want you to be able to look at this structure and identify an organic acid. The key to this is what's called the carbonyl group. It's a C double bond O, also bound to an oxygen. And off that oxygen is bound a hydrogen atom. And then behind it there's this R group, which really is inconsequential. And I'll show you what that means. But let's first talk about why this is acidic. Okay, well, we already know that oxygen is electronegative, so it's going to basically start to weaken this bond because it's going to start to pull electron density away from the hydrogen. Okay, but obviously we know that that isn't that strong of a force because water itself is barely acidic, right? But when you add in the extra pull from this carbonyl group, that delocalizes that oxygen even more and starts to pull the electron density off of it and weaken this bond even more. So consequently, that proton can snap free and leave behind an acetate ion. And that's not a very strong to the right reaction. It's back to the left, so that's why it's a weak acid. So anyway, this motif is always associated with what we call an organic acid, and it's a weak acid. And I put an R in here to just remind you that it doesn't matter what the structure is in here in essence. You know, this is a gross generalization, but to get you used to this. So for example, I have acetic acid. Now I've got a methyl group in there. The thing that hasn't changed is this is still the acidic proton. Here's another way these might be written. Notice in this structure down here how they highlight the C double bond O. They put it in parentheses, and they're trying to say, look, there's a carbon hooked to an oxygen which is hooked to the acidic proton. Okay, and here's another way it gets written with C and two O's and an H. And once again, I want you to get used to knowing that that particular structure refers to that. Here's a better diagram to see the chemical bonding in there. So this particular chemical representation represents this, and so that's the acidic proton. Here's another organic acid, and I wanted to show this one just to highlight that it's not unheard of that there may be more than one acid group on here. So this is a diacid. Both of these protons are acidic. Here's benzoic acid. Now what I'm doing is I'm just changing up the R group. In this case the R is here, this little methyl group in between. Here it's a phenyl ring, a 6-carbon ring. Doesn't change a thing though, this is still acidic. This is the acidic proton. In fact, just to bring the point home, here's a linoleic acid. Look at all this shrubbery out here, all these hydrocarbons. None of these are acidic, it's just that one proton hooked to the carbonyl group. And let me show you one last organic structures just so you realize something that's very similar, but these are different. Here's your acidic proton. Now look how with just one slight change I pull out that oxygen, right? And now I have this structure which is an aldehyde. And that is not an acidic proton. And then I make a change to this where they're both R groups and there's no free hydrogen. And this is certainly not acidic. So my point here is just to kind of show you things that look a little similar because they all have carbonyl groups, but the only one that's acidic is when you have the C double bond O and this other carbon bound to oxygen bound to hydrogen. That's what makes that hydrogen acidic. Secondly, here's a organic base. Okay, so we're familiar with ammonia, and we know that it becomes basic because it pulls a proton off of water and leaves a hydroxide behind. But it doesn't really matter that those are protons. Those could be anything. Okay, the important part is that you have nitrogen with its unpaired electrons, and that's what accepts the proton and leaves the hydroxide behind. And the catch here, one thing you want to identify is in order for it to be basic, nitrogen is bound to 1, 2, 3 things. If it's nitrogen in the acidic form, like the conjugate acid, it's nitrogen bound to 1, 2, 3, 4 things. So that's one of the things you should be able to identify from structure. Is it nitrogen bound to 3 other atoms, or is it nitrogen bound to 4 other atoms? So here's some examples. There's nitrogen bound to 3 things. That isn't a basic nitrogen. There's nitrogen bound to 3 things. And now notice, here I exchange one of the protons with the CH3. This is still basic nitrogen. Okay, now I look at these and I say, oh wow, I've got these nitrogens that are bound to, once again, 1 and 2 hydrogens. That's 3 things. So that's a basic nitrogen, as is that a basic nitrogen. Okay, here's nitrogen. It's bound to 1, and this double bond counts as 2 bonds. So I've got 3 bonds again. So this also is a basic nitrogen. And if I want to change this to the acidic form, all I've got to do is get the conjugate acid, and now I see nitrogen bound to 1, 2, 3, 4. So this is the ammonium ion, and this is acidic. And just for example, if I was to do the same thing with the pyridinium ion, which is nitrogen bound to 1, 2, 3, 4 things, so it's the acidic form, or the conjugate acid. So the key is nitrogen bound to 3, basic, nitrogen, or bound to 4, acidic. Okay, a third thing you need to understand, in General Chemistry 1 you talked about oxyacids, so a strong acid like nitric acid or sulfuric acid, and we never really spent a lot of time explaining where those protons are attached to the acid. So I want you to understand that oxyacids are connected through the oxygen. So nitric acid, literally, here's the Lewis structure of that, is actually bound, the acidic proton is actually bound to an oxygen. And that's really important, because if you look at the structure, once again, just like we showed you earlier with the weak organic acid, that electronegative oxygen starts to pull the electron density in the bond over, which starts to weaken the bond. But there's more oxygens present, and those further delocalize that electron density and weaken that bond, so that makes it acidic. So at this point the pKa is -1, it's less than 1. So now I go over here to sulfuric acid, and I've increased that by 1 more oxygen, so now I've got a pK1 of -3, and remember again that this is pK1 because we're talking about taking off the first proton. Always keep in mind, once you've removed the first proton, that's going to lessen the effect. Okay? So once that proton is gone, now all of a sudden I'm going to talk about how this electron density is getting shifted off of this particular oxygen to hydrogen bond, and that is enhanced by these 2 oxygens. But now I have this negative buildup over here from the deprotonation, and that actually starts to delocalize that electron density back onto this hydrogen-oxygen bond. That lessens the effect. So you may not remember all the electron movement, but just the general rule of thumb is this: the more oxygens, the stronger, or the more acidic, right? The more oxygens, the more acidic. And as you begin to remove the first proton, then the second proton comes off harder. In other words, it's less acidic. Okay, so this is actually still acidic, but it's considered a weak acid at this case. So here we can kind of diagram that with some acids we know about. Here's nitric acid, and here's nitrous acid. Now, because we've lessened the number of oxygens, still the same number, just a single proton, look at how the pKa has changed. It's become less acidic. Now we come up, do the same effect again. Here's sulfuric acid. The first pK1, the first proton being removed, is a strong acid. It comes off very easily because of all the oxygens weakening that bond. But when the second proton's coming off, it's been lessened because of the negative charge that's starting to build up. So that second pK, a weak acid. And then if you start here with less oxygens, you're immediately at a weak acid. It's, instead of made from the sulfate, it's made from the sulfite. So this is sulfurous acid. And once again, because of less oxygens, that first proton is a little higher pKa. It's a weak acid. And certainly the second one is even weaker still yet. So here we can go to phosphoric acid. And now the thing that's changed is we've actually got more protons involved. This is a little less electronegative, and in essence you've now made something that was a instead of being a strong acid, this is from the get-go a weak acid. It's got a pKa of 2. You start to remove protons and it gets less and less. Now when we get into classifying acids and bases, I'm going to show you a little a trick to kind of identify whether it's weak or strong, and just do that qualitatively without knowing these actual pKa's. But obviously if you go to the pKa's, you'll know the answer. So I hope this is helps you get some background to understand acids and bases, and we're going to use this background now in the next video to help you identify strong, weak acids and bases out of a lineup of different materials.